Let us now apply our magnetic design knowledge to the design of transformers. Essentially, the transformer and the inductor will appear very similar physically. It will also have a core, it will have winding, former, all those things. What essentially is the difference is in the BH characteristic. So let me just point out to you the main differences in the BH characteristic of the transformer and that of the inductor. So let us say we have a BH graph here for the transformer, and let me have another graph here, BH graph here for the inductor. So in the inductor, the main focus, main job is to store energy. So energy storage is the main issue in the inductor. We want to store as much energy as possible. In the case of the transformer, it is power transfer, instantaneous power transfer from the primary side to the secondary side. So this is the main job in the case of the transformer, no energy storage. So in the case of the inductor, in order to have as high energy storage as possible, we discussed that we would like to have the mu, the permeability, as low as possible. So it is designed, the core is designed to have as low mu as possible so that you have very high magnetization current here. The magnetization current Ni by Lm, the I part here should be very high so that the energy that is stored in the core, maximum energy that is stored in the core is half Lim square. So more energy gets stored because the energy is proportional to the magnetization current. Whereas in the case of the transformer, we are not talking in terms of energy storage. There is no energy storage. We don't want energy storage. It's only instantaneous power transfer. So we would like the mu permeability to be as high as possible. So if you look at a transformer core BH curve, it will be like this: very high slope for the inductor, very low slope. And because of this high slope, you will see that the magnetization, to reach the same BM, you will need much lesser current. The Ni by Lm, less magnetomotive force or less electrical current I, or magnetizing current I, is needed to bring the transformer core to a level, operating level BM or even BSAT. So we have to design the transformer to have low magnetization current. So that is the essential difference. A transformer is a power transfer device, whereas an inductor is an energy storage device. And when you design, we would like to design transformer with low magnetization current, whereas in the case of inductor, we have high magnetization current so that the energy that is stored within the core is high. So with this fundamental and main difference, let us look at the transformer again in terms of the area product and arrive at the design equations. Let us now discuss the area product relation for the transformers. Now consider a generic transformer which has a primary coil and a secondary coil like this as shown. You have the dot polarities. Primary, the voltage EP measured in this fashion. Secondary potential EMF measured ES in this fashion. Primary has NP number of turns. Secondary has NS number of turns. Primary current IP flows in this fashion, and secondary current IS as shown like this. So if I take the primary induced voltage EP, so it is given by Faraday's law, NP into d phi by dt. d phi is the flux in the core here. Now the voltage here, okay, it's not only the voltage, it's the volt second that we have to be bothered about. So let us take some arbitrary wave shape. Let us say we have a sine wave. This is a sine wave transformer. Let's say the voltage is sinusoidal in nature. Okay, so this is the halfway mark here. This is Ts by 2 and this is Ts by 2. So if it is supply frequency 10 millisecond and 10 millisecond. If it is switching frequency, whatever the switching frequency, that switching period by 2 and switching period by 2. Now we are not that much interested in the wave shape as we are interested in the area under the curve, especially for design of the transformers. We are bothered about the volt second or the area under the voltage profile, this one. So this volt second we need to be worried about. Now this volt second and the equivalent square wave volt second here, let us say we have an equivalent square wave flat top. Both these will have the same volt seconds, let us say. Then what is this flat top value? That will be the average of this particular wave shape. So whatever be the wave shape, whether it be a sine wave, whether it be a square wave, whether it be any other triangular wave or any other arbitrary wave shape, take the average of that, and for the half period it will be equivalent to a square wave with a flat top, and where the height is nothing but E primary average, because the volt second is the same in all these cases. And this average, remember, is not the average of the entire cycle. The average of the entire cycle is 0, because that is very important. The average of the entire cycle in the steady state for across any coil will always be 0, because volt second balance will be there. You are taking the average for half the cycle. This is a half cycle average. Keep that in mind. Okay, now let us see how we are going to get that. dt, we will integrate EP with respect to dt, and this also with respect to dt, which becomes d phi. Then EP with respect to dt and NP, phi can be written as AC into flux density. So therefore area of cross section of the core into dB. Now integrate for half the period only, 0 to Ts by 2, 0 to Ts by 2. So in Ts by 2 time, how much will the flux density vary? It will vary from minus Bm to Bm in most cases, but there are cases like forward transformer where it will vary from 0 to Bm. We will say 0 to delta B, and then we can make delta B as 2 Bm or Bm accordingly depending upon the topology used. So let us say some delta Bm, which is a variable quantity. So in Ts by 2, in half a period, there is a change in the flux from 0 to delta P. Now on integration, you will see that this is a square EP average into Ts by 2, and this is NP into AC into delta B. So now rearranging, you will get NP is nothing but EP average, half cycle average, remember that, 2, then you have AC, core cross section area coming down, delta B, and Ts will be written as Fs. Ts is in the numerator, will make it as Fs. Now this is the relationship between the turns and the half cycle average of the voltage across the primary or any coil, AC, delta B and Fs. Likewise, for the secondary also, you can write it down. Ns is nothing but secondary half cycle average, Es average, to AC delta B within the core into Fs. So you see that there is now a relationship between AC, the core cross section area, and the volt second or the voltage. So AC gives an idea of the voltage supporting capability or the volt second supporting capability for the transformer. Next, let us talk about the window area. kWAW is the available window area. Just like in the case of the inductor, we have loss of window area due to coil former thickness, we have to insert coil former into the core, and then the thickness of the coil former, that amount will go unavailable for the windings. So that much amount decrease in the window area is there. Not only that, when you have circular cross-section coils wound, there is always air gap in between the coil sections, and that will eat away some area. Apart from that, we have seen that enamel over the copper. Copper cannot be just pure copper, because copper will come in contact with the next turn, and then there will be short circuiting of the turn. Therefore, you need to insulate, and therefore copper is normally available as enameled copper. There is insulation which acts as an insulation and avoid short circuit between coils. Now this enamel has a finite area, and that will also eat into the available window area. Now in the case of the transformers, there is another additional loss of area, and that is due to interwinding insulation. Normally transformers, at least minimum 2 windings are there, one primary, one secondary, and in some other applications you may have multiple secondaries, in which case for every winding there has to be an insulation between that winding and the one previously wound. So this interwinding insulation can eat up a significant amount of area. So the available window area is much lesser than that for an inductor. So Kw is will vary between 0.2 to 0.4. In the case of the inductor, Kw varied between 0.4 and 0.6, but in the case of the transformer, because of the additional loss of area, the Kw or the window factor will vary between 0.2 to 0.4, and no wise unskilled winder should use 0.2, and a very skilled winder will use 0.4. So therefore, the available window area has to be used to accommodate NP, primary number of turns, into the wire cross section of the primary wire, plus NS number of secondary turns, plus wire cross section of the secondary wires, if it is just a primary and the secondary. But in a general case, there can be multiple secondaries. You can have a primary, secondary 1, secondary 2, so on to secondary M. In such a case, KW, AW should accommodate NP, wire cross section area of primary, plus NS1, wire cross section of secondary 1, plus NS M into wire cross section secondary M, so on. So that is something that will let us now take just these two, primary and a secondary, and we see that NP and wire cross section of the wire can be calculated from the RMS current flowing through that, let us say IP RMS by the current density J, just like as we discussed in the case of the inductor windings. And secondary, you can calculate NS into IS RMS by J. So now NP, we saw NP and NS, we have a relationship here with respect to the half cycle primary average voltage and half cycle primary secondary average voltage. With respect to the other parameters, core cross section area, we will replace it here accordingly. So EP average by 2 AC delta B Fs IP RMS by J, plus for NS I will put ES average, half cycle average, 2 AC delta B to Fs into I secondary RMS by J. So now you see here AW, AC, AC. Now let me bring AW and AC as a product to one side and then put all the remaining terms. So you see that the denominator here, 2 AC delta B FSJ, 2 AC delta B FSJ, take it out common. AC and AW keep it on one side. KW bring it down. So you will see 2 and KW I'm bringing it down, delta B, J, Fs, all this come in the denominator. In the numerator, summation of the half cycle averages and the RMS currents. So EP average is the half cycle average into IP RMS, ES average, half cycle average into IS RMS. So this is the generic equation for the area product. If there are multiple secondaries like here, so on it will. The half cycle average of that across that particular winding and the RMS current through that winding will come depending upon as many windings that are there. Now this is an important relationship, a general area product relationship for any given transformer, and we just have to calculate EP average and IP RMS and delta B for specific applications of the transformers, and you will get the area product for that specific application. Let us find out what is the area product for sine transformers from the generic area product relationship that we just developed. The area product, generic area product is given in this fashion. We have here on the primary side EP average, half cycle average, IP RMS, E secondary, half cycle average, IS RMS, and the denominator portion given by the winding factor delta Bj and Fs. We need to find out for sine transformers what is the EP average, ES average, and delta B. So let us look at delta B first. If you take the BH characteristic, and let me say that a typical BH characteristic is something like that one. This is plus BSAT minus BSAT, and let us say the transformer flux, the flux in the transformer core swings from a positive BM value to a negative BM value minus BM, and that is plus BM. So which means total swing, so for every cycle it will go from minus BM to plus BM and then back to minus BM, which means in a TS by 2, half the cycle it would have traversed minus BM to plus BM or plus BM to minus BM. So at delta B of 2 BM, BM minus or minus BM, 2 BM swing it will undergo in TS by 2 time. So this portion gets replaced with 2 BM. Next, so that is 2 BM. Next, for the averages here, if you take a sine wave, typically if you think of the half cycle average, if this is Vm sine omega t, average EP average for the half cycle will be 2 Vm by pi, and we know the RMS value is Vm by root 2, and the relationship between RMS and the half cycle average will be 1.11 times P average. So therefore EP average will replace by VRMS by 1.11. Likewise, the secondary average by V secondary RMS by 1.11. So we can take that out common. So let us make that substitution. So AP is V primary RMS into I primary RMS plus V secondary RMS into I secondary RMS divided by 4.44. How does 4.44 come? This is 1.11 because this is V RMS by 1.11. There is another V secondary RMS by 1.11 that will get taken common, come down, which will become 2.22. Delta B is having 2 BM, so it becomes 4.44. Then KW, this is BM, J, Fs. Now V primary RMS and V primary RMS into I primary RMS is the power on the primary side. V secondary RMS and I secondary RMS is the power on the secondary side. We will call this power as P naught. So for the transformer, this is the P naught, V secondary RMS into I secondary RMS, all sinusoidal quantities, and Pi is V primary RMS and I primary RMS. Pi we can say is P naught by efficiency, and generally the efficiency of transformers are much higher than 80%. If we take a conservative value, worst case value of 80%, then we will be rating the primary for P naught by 0.8, and that is very, very conservative. Generally the efficiency of the transformer is much higher, and therefore if we design for a primary side V primary RMS and I primary RMS of P naught by 0.8, we will definitely be on the safe side. So therefore, AP will become P naught by 0.8 plus P naught divided by the denominator kWBM_JFS, and if you simplify that, becomes 2.25 into P naught divided by 4.44 into kWBM_FS. Now that becomes the area product for sinusoidal transformers. It can be used for low frequency operation for where you are using for rectifier, capacitor, filter, power supplies, where you have to step down 230 volts to 18 volts. You can use this relationship for the design of those transformers because they are sinusoidal operated, where Fs will become 50 Hertz. You have to use CRGO, cold rolled grain oriented silicon steel, as a core material, which has a BM of 1 to 1.1 Tesla. Now let us take another example, and that is of a switched mode DC-DC converter. We have studied and discussed the forward converter. Let us try to find the area product of the forward converter transformer. We use the generic AP formula, AP E primary average half cycle, IP RMS plus E secondary average half cycle, I secondary RMS by 2 kW delta B, J and Fs. First, delta B. In the case of the forward transformer, we know from the BH, I'll write the BH curve. So you have the typical BH curve of the core. The swing in the B is from 0 to BM only, because in the case of the forward converter, the forcing voltage is applied only in one direction, unidirectional, and therefore it will swing from 0 to BM and BM to 0. So in at TS by 2 time maximum, it will swing from 0 to BM, and therefore delta B is nothing but BM. So this will be BM. And now for the voltages across the primary and the secondary. So let me show you again the waveform that we had drawn for the forward converter. Let us recall that. Observe, this is the forward converter. Observe the voltage across the coils, forward converter, transfer, primary and the secondary. When the switch is on, the voltage across VP is VI, flat, and across the secondary it will be N times VI. And when the switch is off, of course the freewheeling power portion will come, and the area will be same as VI into DTS during the secondary, during the portion of the time 1 minus DTS. So I will use that equation that during the time when the switch is on, and let us say for the forward converter, the maximum on time or maximum DTS or D can be 0.5. So during the time TS by 2, when this is on, you will see the voltage across the primary as VI, voltage across the secondary will be N times VI, and that would be the half cycle average, whether it will be during the on time or during the off time. So going back here, let us write it down. E secondary half cycle average NVI during TS by 2. I secondary RMS, the current that is flowing through is I naught during that time, and the RMS value is into root D. So E secondary average into IS RMS is nothing but NVI into I naught into root D. Let me multiply numerator and denominator by D. Then NVI I naught. NVI into D is nothing but V naught. NVID is V naught into I naught, that is P naught, and root D, and this root D will cancel, so you will have in the denominator a root D. And if you consider the maximum operating duty cycle, D will be 0.5, and therefore you will have it as P naught into root 2 for D max as 0.5. Likewise, for the E primary half cycle average into I primary primary RMS current, you will find that it is P naught by P naught into root 2 by efficiency, and if I take worst case efficiency 80%, P naught by 0.8 into root 2 will be the E primary average and I primary average. Let us replace it there and see what is it that we get. So this would be P naught root 2. I will take it out common in both the cases. You will have P naught root 2 in both the cases. Let us take that out common, and it will be 1 by efficiency plus 1, which is 2.25, and the denominator 2 kW delta B JFS. So this portion 1 plus 1 by 0.8 is 2.25 into P naught root 2 and this 2. So I will replace in the denominator root 2 into kW Bm JFS. So this would be the area product of a forward converter. So let us use this area product and do an example. Before we work out any example for transformer design, let us write down the design steps. There were many equations that we discussed and developed. Let us sequentially list down all the equations, relations that are necessary to design the transformer, and step by step write them down. Step 1. First, let us estimate the load power P naught. Estimation of P naught. This load power for the transformer is all the secondaries put together. So P naught should reflect all the power in all the secondaries if it is a multiple secondary transformer. So let us say in a more generic sense, if there are m secondaries, I is equal to 1 to m, 1 by t integral of 0 to t voltage across every secondary, ith secondary, current through ith secondary dt. So this will give you the average power of every winding, will give you the average power of the ith winding, and iterating I from 1 to m, all the windings average power is obtained and they are summed up to give you P naught. Next, step 2, area product. Because the area product needs the P naught value, we need to use the P naught of step 1 to find out the area product for the particular application. Then after you find the area product using the area product for the particular application, select a core from the core table. Just like we did for the inductor, after the area product you have to go to the core table and then select a core which is having an area product higher than the calculated area product. Then after having selected, note down the core cross-section area AC and window area AW of the selected core. Next, step 3. So in step 3, we have to evaluate the number of turns. So NP, we know we have this relationship, the primary voltage average, half cycle average, divided by 2 AC delta B into Fs. Secondary windings Ns. The ith winding is given by the voltage of the secondary of the ith winding average half cycle divided by 2 AC delta B Fs. And the turns ratio of the ith secondary winding with respect to the primary is given by NSI by NP. So this is the turns ratio of the ith secondary winding with respect to the primary. Step 4. Next, we find the wire gauge. We have the turns ratio, we have the number of turns to wind, we have the core. We now need to choose the wire. What is the thickness of the wire? So wire gauge selection, like in the inductor, the area of cross section of the wire, the primary, is given by the IP RMS current flowing through the primary, by J, the current density. And the area of the wire, cross section of the wire of the secondary of the ith winding will be the RMS current of the ith secondary winding divided by J. So like that, for every winding, you can find its RMS current and divide by J, you will get a calculated value of AW, wire cross section area. J, what you are going to use, just like in the inductor, we start with 3 amp per mm square, or 3 into 10 to the power of 6 amp per meter square. After having calculated AWP and AW, all the secondaries wire cross section area, go to the wire table and choose the wire gauge from the wire table. After having chosen the particular SWG, standard wire gauge, note down the values of the actual wire cross section area of the primary and wire cross section area of the secondaries. This would complete the design, but there is one more step needed to complete, one cross check step, just like we did in the inductor design, window area cross check. KWAW, that is the available window area, should be greater than NP, primary number of turns, into the wire cross section area of the primary, plus apply for every secondary winding, secondary number of turns of the ith winding into area of cross section, wire cross section of the ith secondary wire, and add them all up. All these turns into area should add up and fit into the available KWAW. Only then the design will be successful. If this inequality is not satisfied, you go back to step 2. Select a core, another core having a higher area product, and then repeat all these calculations for step 3, step 4 again, till step 5 inequality is satisfied. Then the design is successfully completed.